Hi, I'm Jeremy Gebben. I've been at LunarG for about 4 years. I work mostly on validation layer. I've also worked on the synchronization to emulation layer. Before that, I was a kernel mode driver developer working on some of the early Android devices. And we used to like to say that GPU hangs roll downhill. So user mode driver bugs, they always involved the kernel mode team, so I got to work a lot on this kind of stuff. I also got to work in software architecture and asking the hardware team why we couldn't have nice things to help us debug these kinds of problems. Got a lot of different answers. I've also worked on a lot of non-GPU embedded things where you might have a bank of LEDs telling you what's going on. You might have a really slow serial console, and hopefully everything works. Didn't have a debugger. So this kind of stuff has been, unfortunately, a large part of my career. So Crash Diagnostic Layer is a new tool that's based on some existing work. We'll talk a little bit about that. That is kind of providing glue code for a bunch of extensions to help you debug GPU hangs or device lost errors. It's new in the Vulkan SDK. It's alpha quality. I'm not sure how many people have used it, but it's probably less than 10. It works on many different devices that support these debug extensions, and there's additional Android devices that look promising, but we're not supporting them yet. It's pretty lightweight. I've measured a 5% CPU hit in real game content on desktop, so it should be usable without changing things in how the application works too much. So what can it do? So the big thing it does is track forward progress of your queue submissions and within the command buffer execution. And we'll talk a lot about how that works. It can get fault information from the driver that via extension, the device fault extension. We can also change the command stream. We put in markers to help find forward progress. Can also add pipeline barriers between commands that try to help narrow down the source of a hang or a fault. Dump state in a YAML format, which is yet another markup language format. There's historical reasons why that is. But it's machine readable, and it looks pretty good to humans too. The big thing that this tool can't do is we can't debug within a shader invocation, and there's just simply not information available at the API level to let you do that. That's all secret sauce, registers inside the GPU. Vendor-specific tools can do this in some cases with mixed results, I would say. So these are the main extensions that this tool uses. It also uses timeline semaphores. We'll talk about that. AMD Buffer Marker and NV device diagnostic checkpoints are used for forward progress within a command buffer. Device fault and device address binding report are used to interpret fault information coming out of the GPU. And then the device coherent memory is a bonus extension that helps with the reliability of the AMD Buffer Marker. So what happens when you crash a GPU? Depends on how well the OS and the driver and the application are working. So you might get an error dialog. You might lose access to the GPU for a while, like my test program does when it crashes the GPU 10 times in a second. That makes Windows angry. Sometimes you lose the screen forever, sometimes just for a little while. Sometimes you get locked out of your X session. Sometimes the whole device crashes or gets really warm for strange reasons. Usually, these days, we're towards the top of that list and not at the bottom of that list, but when I started working on graphics, that was not the case. So what happens in your app? You do something, you'll get back a device lost error, and you have a choice. You can restart rendering, and for things like compositors or mobile UIs, that's probably what you want to do. For a game or just a normal application, you might want to exit nicely, gather some debug information and send it off and tell the user what happened. Or you can just crash. That's always an option. So what happens in the driver? Drivers are looking at forward progress, like I said, so they'll have some sort of timeout, and that's usually what we call a GPU hang. And there's also various hardware interrupts that might happen, telling you that the GPU is in a bad state or you got a page fault. And when that happens, GPUs are now multi-user applications. They might be, like I said, a compositor, other applications running on the GPU in a time slice manner. So the driver has to figure out which application caused the fault, return device loss to that. Then we have to reset the GPU hardware. Sometimes that's removing and restoring power to various parts of the chip. And then continue on like nothing happened as best we can, and keep the other innocent applications running so that the user has a chance to do something else. So debugging crashes has always been really hard, in my opinion. I think most people would agree. Part of that is historical. Before Vulkan, any crash was a driver bug, and that would be something that we tried to catch before the device went out the door or before a software update happened. It was the driver's fault or the hardware's fault, and we had to fix it. So we had to put in a workaround, make sure that everything was valid at all times. Just a lot of drama, and it wasn't something that end users were ever supposed to see. Another thing out of history was that, I mean, the first use cases were full screen games, and we didn't really have concurrency on the GPUs, and so the fault recovery and figuring out who was guilty and who was innocent and continuing on wasn't really a hardware or software feature. You just kind of restarted where you were and moved on. Another part is just the fundamental nature of the beast, which is massive concurrency. If you have a problem in a shader and there's a million fragments going through that shader, how do you step through that? How do you single step through that like on a CPU program? You can kind of see this with multi-threaded, where if you have 32 threads cooperating and you start single stepping, you're going to change the behavior of the program enough that your crash might go away or it might happen differently. Last one is unfortunately IP. A lot of these details for most of the history have been locked up, not publicly available. So you didn't always have the information you needed to know how to debug these things without talking to someone with access to the secret sauce. There's also, I would say, bigger differences in architecture between GPUs and CPUs, so there's a little bit more of complexity of figuring out how a device works and how to debug it. And sadly, in my experience, debug features, they don't win. If there's a choice in the schedule between improving performance on a benchmark or reducing your power budget, that's going to win over a debug feature most of the time. And that's kind of where we're at. It's getting better, I'd say. So let's talk about this tool and how you use it and what it can do. So the quick start is get the SDK, start up vkconfig. There's a pre-baked configuration for this layer, and it'll give you the screen on the right and with all the settings. These are the defaults. We'll talk about some of the settings, and other ones like message severity should be self-explanatory. Crash something, and then it'll write files to the file system, and you can look at those, and we'll talk about kind of what they look like. And then when it doesn't meet your needs, file issues. This is a new thing. It's gonna require some tweaking to get it to where it really helps people, I think. So when the layer's enabled, there's a bunch of logging that comes out. The most important message is here at the bottom, where we encountered an error and dumped out a file, and there's the path to it. And if you keep crashing repeatedly, you'll get a new timestamp directory so that you can look at all of your crashes and decide if they're the same or if they're different, because that can be useful. Kind of depends on the nature of the crash, whether you get the same thing every time or you get kind of random results. So let's talk now about what's going on under the hood and making this work. So the big concept is forward progress, and that's evidence that the GPU is still doing something useful. So that means you're moving forward through queue submissions and through command buffers and not getting stuck inside one shader forever, which could be an infinite loop, or it could be the hardware in a bad state. In the driver, we usually have interrupts that are telling us things are happening. That's how you signal fences and semaphores. There's also usually counters that will be changing, and there'll be timeouts that are detecting when things have stopped happening. In application, you're a little bit more limited. The wait idles don't really ever time out, so unless the driver has some sort of timeout baked into it, you could get stuck forever. So usually there's a timer behind that'll stop you. Timeline semaphore and fence state changing is another good clue, and this layer makes heavy use of timeline semaphores to look at forward progress. There's also a Watchdog timer in the layer that is keeping track of what's going on, and the assumption is that if you stop submitting work at the application level, that means something is hung. You're not getting back the results you want, so we'll assume that the GPU is stuck somehow and try to make a dump. You might want to turn this off if you're using the debugger, because that'll stop the time and you'll probably time out. So if you're stepping through your code in the debugger, the Watchdog timer is not your friend. Some drivers have their own Watchdog, most probably do. If you're getting good results out of that, you might want to turn this off or lengthen it. The big advantage there is if the driver implements device fault, their Watchdog will probably pull information out of the hardware and let you query it with the device fault through the layer, and that'll give you more information than if this thing just stops and dumps without waiting for the driver to time out. Then there's compute jobs or kind of reactive rendering where the GPU might be busy for a while, or it might be idle for a while, and that might interfere with the timer. So at the command buffer level, like I said, we use a timeline semaphore to do forward progress tracking, and it splits up each submission into multiples that are much simpler. So we'll have a single submission for the wait semaphores if they're present, and then each command buffer in the submission will get its own submission with a timeline semaphore that's incremented after that. So there's a per queue semaphore that's trying to keep track of how far we've gotten in the work that's been given to the GPU, so that later we can go back and figure out what happened. This is also used to retire state. Like that's probably most applications do use timeline semaphores for stuff like that. Since we're keeping all this state around, when it's completed, we want to throw it away, and this is how the tool does it. Within a command buffer, there's a concept called checkpoints, and there's two different implementations of these that I'll talk about. These are trying to keep track of what's going on as the GPU processes a single command buffer. So remember that multiple commands can be executed in different parts of the GPU at the same time. So we have a top of pipe and bottom of pipe stages that are can tell you what started executing and what's complete. And so if you crash, these two checkpoints will be at different points within the command buffer, and that'll give you a window of commands that are possibly where the crash happened. So for the AMD Buffer Marker extension, which again is implemented by several devices, not just AMD, but they kindly made it for us. We have these write buffer marker commands, and you specify a stage, which is top or bottom of pipe, and that just lets you write whatever value you want into a Vulkan buffer, and when the GPU hits the stage, that value will be present in the buffer. The device coherent memory extension, which is only supported by AMD as far as I know, is pretty important, because that makes sure those writes get out of the GPU's caches when you're crashing. So you'll get much more accurate results if that extension is present, because you avoid the caches. The other nice thing about this extension is that if your command buffer completes entirely, all the values in memory or all the values in your markers will be written out. The next extension works a little differently. So NVIDIA's extension, which I think is also implemented by Intel, you just have the single set checkpoint command, and it implicitly keeps track of top of pipe and bottom of pipe for you. And then later, after a crash, you can call the get checkpoint data, and that'll tell you the most recent checkpoints. When you're crashing, this is usually pretty accurate, but if your command buffer completes, those checkpoint writes are just kind of gone. You never see them. So that's part of why this tool has timeline semaphores to keep track of which command buffers were successfully completed. So this is what it looks like in the dump. Each command has an ID and it has a checkpoint value, and then we print out these little banners that say this is the last command that we know was completed, and this is the last one that started. And you'll notice that there's a gap in the IDs there, so there's a window of commands that could have been the cause of this hang. And ideally, we want this window to be as small as possible, because then you know if it's one, you know where to look, and if it's more than one, you have some searching to do. The other part of the tool is GPU faults. So almost all modern GPUs have an MMU, and if you do a bad memory access, just like on the CPU, you get a page fault. The device fault extension returns that back to the application. Previously, that would probably get eaten by the kernel mode driver. Maybe they'd print it out to the kernel log or some other mechanism. The other part of this extension that we implement, but it's not widely implemented by drivers yet, is vendor-specific fault information. So this is where a vendor could choose to put in a register dump or any other information they know that's not explicitly part of the extension and that's specific to their hardware that might help you interpret what happened. The RADV driver does this. I'm not yet aware of any others that are doing it, but it's a good feature. I know some of the mobile GPUs have this kind of stuff in the, but I don't know if they have it in the extension yet. And then device address binding report is a notification that comes every time the GPU address space changes. So this lets you build up a database of all the addresses that are in use on the GPU, so that you can know where which Vulkan objects are associated with a fault. So I've got some examples of different kinds of faults. Buffer overrun, if you read past the end of a buffer in this case. So we have an invalid read. We have a range of addresses that could be associated with the fault. The hardware doesn't really tell you always exactly what address you read. So it's a range. And in this case, the begin of the fault range is the end of a device memory record that's currently bound. So that's most likely you read off the end of a buffer. Use after free. Here we have the begin range of the fault is matching a begin range of a record that's not currently bound anymore. So you freed this memory too early, and the GPU unmapped, or the driver unmapped it from the GPU, and then you get a page fault. And then the last case is just a garbage address where we have this bad dead address. There's nothing in the database that's near it. So that's uninitialized memory of some sort. The next big feature, which is really helpful in some cases in terms of narrowing down which command causes a fault, is this sync after commands feature, which adds pipeline barriers after commands. Any command we put a checkpoint after, we then put a pipeline barrier after that, and that effectively idles the GPU between these commands. And in one case, one of the sample crashes in a real application that I got, this reduced the number of running commands from 180 to 1. So that gives you a really strong indication of where to look for the fault. And then, it reduces the amount of searching. The downside of this is it's going to be slower because you're idling the GPU, and it's going to cause some crashes to go away. And those are usually, if you're missing synchronization, this is the biggest possible barrier inserted between every command. So all synchronization problems will go away. That's when you go look at synchronization validation. So the way this works, and it only works for dynamic rendering at the moment, is when you get a begin rendering call, the rendering info gets copied. And then later when we get a command with a checkpoint, like a draw, there's several other commands that have checkpoints after them. We'll do an end rendering, pipeline barrier, and restart rendering with a slightly tweaked version of the original rendering info. Can't have full pipeline barriers within a render pass. This could work for real render passes, and how I'd probably implement it is to break each subpass into its own dynamic rendering pass, and I mean, then you're again reducing the benefits of a tiler, but that also helps you isolate problems. You have just one render pass on the GPU at a time. That'll make some crashes go away, but that's good information too. But that's not implemented yet. It's something for the future. So this layer integrates with the debug utils like you'd expect. It also integrates with layer settings, so you can control it from your application programmatically. You'll get any names you put on objects will show up in the crash. It will also send all our log messages to the debug utils callbacks. So it should play pretty nicely with all of the other Vulkan tools. And that's it. So I'm going to be doing a demo at the reception. I have a couple different systems that have the crashes to run on them, and I can show you more details of the log file or answer questions. Like I said, this is in the new SDK. It's on public GitHub now as of about a couple weeks ago. And as I mentioned, this did not start from a vacuum. This started from a Stadia tool called Graphics Flight Recorder, and that got abandoned when Stadia ended about 2 years ago. It was a great starting point. They had a lot of good ideas, and the new extensions have been added to it, and it's been a lot of cleanup work to get it to where it is now. But I mean, that's the beauty of open source. If a project ends, it's not gone into the vapor forever, and you can pick it up and dust it off and turn it into something new. So big thanks to the guys who developed that. And that's it.